Let's work the following problem. We have this integral that's defined by the integral between 0 and x of t to the power n e to minus t dt. Here we have x is bigger than 0 and n is greater or equal than 1. The aim here is to prove that the limit of f of n of x exists all the time as x goes to infinity. Okay, how can we do that? So one way to do this is that we can use induction. Okay, so we're gonna use induction and by first noting that when n is 1, we can easily integrate and take x to infinity. Okay, so in this case we obtain 1. When n is 1, the value of this limit is 1. When n is 2, the value is 2. Okay, when n is 3, the value is 6. Okay, you can try that and work it out by yourself. Here we can use an induction to prove this result. Okay, but we need to have a link between fn and fn minus 1. To have that, we're going to use an integration by part. Okay, first we're going to do the following. We're going to differentiate and integrate. We're going to differentiate t to the power n, and we're going to integrate e to minus t. Here we have n t n minus 1, and here we have minus e to minus t. Okay, and therefore we get our formula here. So doing that, we get fn of x is minus tn e to minus t between 0 and x plus n t to the power n minus 1 e to minus t dt between 0 and x. Okay, when we do evaluate here, we're going to get minus x to the power n e to minus x plus n, the integral between 0 and x of t to the power n minus 1 e to minus t dt. Now we can use our definition here. So for n equal, when n is 1, we said it's 1. Now to use the principle of mathematical induction, we assume that here this is f, let me write it here, minus x to the power n e to minus x plus n fn minus 1x. So this is the key here. Okay, so now we have a link between the induction hypothesis and what we want to prove. So we assume that the statement that this limit exists for n minus 1 or for n, and we can prove that it's true for n plus 1. Okay, but here we can assume that it's true for n minus 1, and we prove that it's true for n. The same thing. Okay, so we assume that it's true for n minus 1, and we want to prove that it's true for n. Okay, so here, since it's true for n minus 1, this limit exists. Okay, so this limit exists. Okay, so if we denote this limit but by un, okay, let me write this one. Let's denote this limit here. Okay, here the limit of fn of x as n goes to as x goes to infinity, as let's say as a sub n. Okay, here we have an is minus x. Before we do that, we have to take the limit here. So the limit, because we haven't taken the limit here. Okay, So that's what we're going to prove. So here we say the limit here, the limit as x goes to infinity of x minus x to the power n e to minus x plus n a n minus 1. Here, with this limit exists, we assume that it does exist. So the limit as x goes to infinity, we call that one n minus 1. Okay? And here, we need to prove this limit here. That's the key. So what's this limit as x goes to infinity? So we can prove that this one is 0. Okay? And we have proved that using the L'Hopital's rule. So this is 0. Therefore, we have an is an minus 1. Okay? Since this one exists, finite, this one is finite as well. Okay? And therefore, by the principle of mathematical induction, the limit as x goes to infinity exists, and it depends on n. Okay? And that's how we prove this result here, by just using induction. Okay? And in fact, we can use this result here to prove that an is n times n minus 1 times an minus 2, and it's n times n minus 1 times n minus 2 until a1, and we get n factorial. Okay? In fact, this limit here is n factorial. Okay, we see it from here. Okay, so we can use the principle of mathematical induction to prove such results. So we had to link between Fn and Fn minus 1, which is the induction hypothesis. Okay, thank you very much.